second meetup of April of KW Intersections, the first time that we actually have 2 meetups in 1 month, which is something special actually. And today we will have Etienne Manderscheid Head of Data Science of TalkIQ, who will be teaching us more about convolutional neural networks that they are using for NLP.
Well, thanks everybody for coming. It's great to be here. So a tiny bit about my background. So I got my degree in computational neuroscience. I did my PhD at the University of Chicago, working with songbirds and their brains, working with syllable recognition, and so I got to learn a little bit about speech recognition techniques that I was applying then to song sequences that birds produce, and some machine learning techniques that I used there as well. In that regard, me really interested in syntax and natural language processing problems in humans. And so I co-founded TalkIQ with Jim in San Francisco, and the company has grown, and we were very lucky to find this community out here because there's a tremendous amount of talent. And in San Francisco, it's become very difficult to hire talented people. There's just so much competition, so many big companies going for people that it's difficult for startups to grow. So we feel very fortunate that we found this community. So what TalkIQ does, does a number of things, but at the highest level, we strive to improve the quality of conversations. So we do speech recognition, we acquire audio through the telephone, we transcribe the audio, and then we do some natural language processing on top of the transcripts to yield some insights back to the customers. If you think about the problem that a sales organization or support organization faces, they have hundreds of reps every day making usually hundreds of calls each in some cases. And that huge volume of calls is mostly a black box. There's very little visibility into what's happening in those conversations. And so, we think the time is right to bring that corpus essentially online and analyze it. So the link at the bottom there, if it wasn't so late in the day, I would be able to click and show you calls happening in real time. But right now, salespeople have left their desks. So I will just show you a picture that we took. So this is an example from our real-time application, which we developed fairly recently, in production fairly recently. And so it allows, you can see the two sides of the conversation. So something the customer has said, something the rep has said. So it looks like Jerome is looking for Todd, who's presumably the owner of the establishment. And so a manager would see, 20 or 30 or, how many reps they have sort of going on in parallel. They could click on each one, see the transcript, and they could see important moments in conversations. That would become clear. And so another project that we have is predictive insights. So essentially, I don't know how familiar you guys are with sales, so I won't make any decisions. When you're trying to sell a product and you make a series of calls, that's called an opportunity. And so the opportunity can be closed won, which is a success, or closed lost, which means it's not going to be a success, or it remains open. And so it's it has a lot of value if you can predict whether an opportunity is going to go well and be won or be lost. So that's sort of the center of our prediction, is predicting the health of opportunities. So here's a look at an opportunity. On the x-axis you have time, and you can see the distribution of calls, how they happen. So a very long call early in the opportunity, and then a couple of calls on the same day, and so on. And then a bit of a summary here. So this green arrow indicates we think it's going well, and some of the moments that happened. And so here, just actually some of the, it looked like somebody was saying, okay, talking about another vendor, we flag that as an objection about not needing the products. And this is what's in production. Our models are getting all the time more and more elaborate. And so today we'll be able to tell you what we were doing with convolutional neural networks in the NLP domain to find moments such as these. And this is just staging the problem a little bit, that there's a trillion words that are spoken every day between representatives and their customers. And therefore there's a massive amount of data that remains unmined. and a big opportunity for companies to step in and try to make that data useful. So these are sort of three categories that the problems that we face fall into. Just acquiring the audio, which is actually remarkably difficult. There's a lot of challenges in telephony that come up, routing calls. If any of you are well telephony, then you know it's a lot harder than you think. I won't go into that one today. Speech recognition, which is what we initially focused on the data science team on. And now that it's quite mature, we've turned our data science team onto NLP, which is once you have the text transcribed, how do you get insights from it? And that's the part I'll focus on today. So I'll actually skip through the speech recognition slides right now. I'll just say that we train our own neural networks for speech recognition. So these would be also convolutional neural networks or LSTMs. And if we have time, perhaps I'll come back to that if you guys want to. So as a particular example of something that we do on the NLP side is sentiment analysis. So here we're looking to expose instances of positive sentiment when the customer says something that would lead us to think that they feel positive about the product or the sales process. So it's a little bit different from your traditional sentiment analysis if you were trying to say if something was a positive or a negative tweet, right? Although of course there's some things. And it's, I always like to see this quote that David put out, that you shall know word why the company keeps. I think it summarizes a lot of the algorithms that NLP uses very well, at least for the kind. So this is, I don't know how many of you are familiar with TensorFlow. I expect a few of you at least. But this is a view from TensorBoard of what this convolutional neural network looks like. So this is based on a paper by Kim 2014. And it looks maybe perhaps quite complicated from this point of view, but when we'll break it down, it's actually relatively simple. Alright, so now we'll jump in. So word embeddings are a representation of a word that's a mathematical representation. So everything, of course, that a network processes has to be numbers. So we represent words by vectors. And so in this case, the k-dimensional vector will be representing a word. So there's been a compression. And for those who you can kind of know this, it's not part of the scope of this talk, but we use word to vec. Okay. And so how do you go from a word, which is represented as a vector, to a sentence? So a sentence of length n is represented by a series of columns. Each column represents a word. And so a k by n matrix naturally represents a sentence of length n. So down here, just showing the concatenation of the vector for the first word, the second word, third word, and so on. And that will be the matrix that represents the sentence. And since I mentioned embeddings, here's a visualization of what it looks like. So a nice property of word embeddings is that you can actually find that the vector representations of words which are semantically related are close by in that space. So as an example, this is largely based on the conversations that ZenReach was having in this example, and which is a startup on the third floor. And so they have a lot of conversations about Canada, the expansion, how they recently launched the new branch in Canada, and so all these words tend to co-occur in conversations, and so they cluster very close to each other in that space. They also have an office in Scottsdale and Phoenix, and so Phoenix, Scottsdale, and I mentioned the San Francisco headquarters also happening next to each other. So convolution you can think of it as the simplest level as, in this case, running a sliding window across the sentence and doing an operation, a multiplication operation inside of that window. So for example, to get the first feature from the convolution, we would actually be looking at, so you have a filter that defines a convolution. So the filter would be, it's called W and have size k by h. And that will be multiplied just with the first column up to the I plus h minus 1th column of the matrix. So, in both cases we're taking h columns from the matrix and from the filter, multiplying them, and that will give us the first feature Ci. And then we slide the window across, and we get up to Cn minus h plus 1 feature vectors this way. And that, I think, will become clearer when I show a diagram in a couple slides. Okay, and then, so the way that we then get to a single feature vector is simply applying a max pooling operation over all of those. And that has the advantage that that way we can represent sentences of any length n with the same representation. And a nice property of max pooling is that intuitively it's thought to often capture some of the most important features. The intuition being that the largest feature might be the most important. And so we use more than one filter. So here's some examples of filters of different widths h. So as an example sentence, this was from a corpus of meter reviews, great for the video and for rental. So the rectangle here, that's the matrix that represents the sentence, right? So you have n rows, which represent each of the rows, and then k dimensions for the dimensionality of the embedding. And then this red rectangle here represents the kernel of h equals 2. And as you multiply the kernel by these first two words here, that gives you a single feature vector over there, which is the red square. And then as you would slide it down, you're generating more squares. Then you apply the max pooling operation to essentially get a single square from that vector, and that's what you have over there on the right, the penultimate layer. The final operation is a softmax operation, which I'll explain to you, and that gives you just two neurons. And those will tell you if it, essentially one of them represents positive sentiment, the other one the absence of positive sentiment. So to cover the softmax operation, so there's two things that we do. We do regularization in that penultimate layer. So that's done in two ways. There's so the weights are actually constrained to be no more than a certain L2 norm. If they're more than that, then they're simply thresholded to stay at that value. And the other method is using dropout in the penultimate layer. So dropout was introduced fairly recently, a few years ago, but it's very widely used now. And it's sort of an interesting idea. So during training, you randomly deactivate a number of the neurons. You set their activations to 0. And what that does is that it prevents neurons from sort of counting on each other too much and being too correlated in their activations. And because they can't be so correlated in their activations, it helps them to represent independent information as opposed to having correlated activations. And then the softmax layer, so what we're doing here, so you've got X being the activations of the penultimate layer, and WJ being the weights leading to the class J output neuron. So these are multiplied and exponentiated, and then the term underneath, it's the same form, but you're summing over all the classes in your output. And that gives you the probability that your class is J. And actually some new stuff from David, so if that's all right, David, I'll have you jump up here and give a quick explanation.
Okay. Thanks, Etienne. So I thought often it's, when you're using some of these more complicated architectures, you can get lost easily, and so it's useful to visualize what's actually going on inside of, in this case, the neural network. And so this is what I'm trying to illustrate here. We've seen this picture of the neural network, and on the left-hand side we have the sentence going in. It runs through some filters and layers, and then you predict a class at the end. In this example, is the sentence positive or not? So that's a problem. Now, to picture what's actually going in and maybe get some insight into how the neural network works, we can look at the activations of the neurons within the network as you're feeding the data in. So, for instance, with this neural network, we have 3 filters. And so the first filter, point here, this looks at one word at a time, essentially. So as it's scrolling through the text, the neural network is kind of interpreting one word at a time. And the colors I'm showing here indicate a kind of impact. How important is this word to the classification, i.e. whether it's positive or not? And so white being low and red being high in this scale. So this was a sentence of a real data set. Picked out one sentence here. It's a little bit garbled, as often phone conversation sentences are, but just weren't cool with it, and I'm good man, but I'm really busy today, so we're going to have to da-da-da-da-da. Okay, so this is maybe quite complex to try and classify as this positive or negative. Now maybe as humans we can tell immediately this isn't positive. This guy is, you know, perhaps not expressing too much interest. But if you were to look at it just one word at a time, you would see, oh, there's cool in there, good in there. So maybe, how can we tell? Well, I think the key is you can go to another layer and consider 2 words at a time and scan through the sentence. And as you do that, you can pick up word pairings. And you can see that the importance or impact of the word is now changing or evolving. So now we're picking up words together. So weren't cool, I'm good, really busy today are kind of being grouped together. And perhaps we're going to get a more informed decision at the end in this way. And then finally, we can extend the filters to 3 grams, gram usually meaning word. So for 3 grams, we start to, I think, get a better representation of this word in terms of the word impacts. So, and I'm good, it's picking up I'm, it's kind of attaching it to the individual. I'm really busy today, so we're going, you know, and it's kind of capturing longer sequences which might help inform our decision a little more clearly.
One thing that's cool there, the word really doesn't have any importance in the 1 gram, but by the 3 gram it's a lot more important. And that's a word that only means anything in interaction with the following word. So perhaps that's why it gains impact, right?
Right.
Can I ask a question? Or it's
Yeah.
So how do you know how many filters you should have for?
Yes, so often I don't think there is any gospel or Bible with designing these architectures. So I usually look in the literature, and people have often tested these questions, and they'll use a whole series of architectures with different filters, different sizes, and so on. And they'll often, the work has usually been done already. And so this was an architecture in a paper by Kim in 2014, and some other authors had explored other architectures, and they analysed the accuracy and so on, and they thought this was a pretty good one. That was also relatively simple.
I think another approach with language models. I did some readings a few months ago, and I remember there is research done with like n-gram language models, but they say if you go over 3 gram, you don't get too much information. You know, if you go 5 or 7, it's kind of the same like 3. So.
Yep, seems to be the magic number for language, right?
Yeah, and I guess that's fairly consistent with this architecture here.
Yeah, but then of course they use LSTMs now for language modeling, and I think some papers report as much as 20% improvement in word error rate. But of course could be very long sequences.
I mean, we can think of some sentences where you actually need to go many words beyond 3 or 4 to actually capture the full meaning. But yeah, they can become expensive and noisy, inherently noisy if you're applying that to every sentence you put in, and you're going to introduce more noise.
You have a huge data sparsity issue once you move beyond an N.
But I think by simplifying, you take a risk that sometimes the model. I've seen some videos where it like goes way off of the prediction.
I mean, you can get long distance dependencies in language that are really far away that an n-gram model will never capture.
Yes.
Which has always been known as the weakness. I think it's just they're so powerful though that it doesn't matter.
Mm-hmm.
But I don't know if you can account for that through other features or layers, but I would think would be one of the main shortcomings of n-gram.
Right. Yeah. So with the n-gram, you can see the limitations of the n-gram as you say. Yes, you have this fixed window, but with the convolutional neural network, you can pick up words at a larger distance and you can cluster them together in a self-learning way.
By 2s and 3s, but if there's a word way at the end of the sentence that has a dependency on something at the beginning.
Yeah, it could still be possible. So you could get, you could pick up a high impact, maybe pair of words here, and over here this could be extended 50 words or so, and perhaps pick up a high impact there. And if you had enough training data,
That's true, yeah.
then you could correlate those. But then you start to run into problems with training data. Needing many examples of those kind of scenarios.
I wouldn't find it in a single example, but if you had enough examples.
Yes. Yeah. So there's pros and cons. So I'll talk a little bit about training the model, how we do this in practice. And often this is the bottleneck for machine learning, is acquiring enough labeled data. And when I talk about enough, it's hard to put a number on it, but typically tens of thousands of labeled data instances are required for some of these networks. But one way to maybe kind of bootstrap your network or get it started is you can use publicly available data sets. There's a Twitter data set which contains tweets that are archived, and the tweets must have an emoticon attached, and then there's your label. So if you have a tweet and then a smiley face, you can label it as a positive sentence tweet.
Unless it's sarcasm.
That's right. Yeah, we don't do well with sarcasm.
You own the market to North Americans, right? So.
Yeah. Well, we'll see some of the problems with this in an approach, but at least it's a starting point, because there are millions of tweets available in these data sets, so you do have that, the volumes of data, but the quality of labeling isn't always as good, so that's a problem. Another approach is you can use humans to manually label your data. You can outsource that through services that exist. So there's a service called Mechanical Turk, which you may have already heard of. There's also another one called Scale API, and you just give instructions in an online format, and it will be sent to a human labeler, and they will follow your instructions and give you a label and send it back. That's essentially how it works, and so we've been employing some of that at TalkIQ. And yes, and another data set that's actually common in sentiment analysis is a Rotten Tomatoes data set. So Rotten Tomatoes, reviews are fresh or rotten, and so there's your labels of positive or negative, and there's thousands and thousands of reviews out there, so that's another nice data source. But again, the quality of the labels can be debated.
Do you have a process then to review the quality of the work that you get in? Just maybe take a sample
Yes.
of it? And,
Yes, and we might be talking about that a little bit more towards the end of Cindy's work.
Yeah, absolutely.
Yeah.
So you mentioned the Rotten Tomatoes stuff. The entire corpus of that text is labeled then. It doesn't tell you whether individual sentences are positive or negative. How do you deal with that?
Yes. So some people have thought of that, and some people have picked out just sentences from reviews that are that contain the sentiment, and those are labeled.
Summary.
Yes. So some people some people have filtered the data. Yeah. Okay, but I think this might highlight some of the problems. So, when I trained a model on Twitter or tweets, and I tested the model on tweets, so that is you give it a data set, maybe 1 million tweets, you train it on that, and then you give it a new data set that the model has never seen before. And that might be 100,000 tweets. And you test it, and you see if the model predicts whether it's positive or not. And you can, since you have the labels, you can test it. So in this case, we did that, and you can measure performances like precision, recall, F1 score. This is kind of all related to accuracy, and it's quite good. 80%, I'm pretty happy with that. However, now when I use that same Twitter-trained model, but then fed it in new data, now apologies for the lingo, when I fed real conversational data in, that we had labeled, and I measured the performance dropped dramatically. So you can see the precision goes down, recall, F1 score, all down. So that's not good. So we can't cheat by training it on something else and applying it elsewhere. And we can demonstrate that if I now take the model and use our real data, and I called it Scale API because that's this human labeling service we used. We use that to train it, and we use that data to test it. The performance goes right up again. So that demonstrates the importance of the lexicon, you might say, to training and testing your model. You need to use the right lexicon, the right context to train your model. And hands up if anyone's used a machine or artificial neural network before. Okay, cool. So I just thought I'd provide a little more details for those who have. We use this gradient calculated backpropagation. It's actually a stochastic gradient descent method that we use. So it introduces randomness into the backpropagation. These are the typical training parameters for those that have an eye for detail. Turns out when you train the model, you feed it in batches of sentences in this case. So you feed it like 10 or 20 or 64 sentences at once, and that way you can kind of speed things up. We run through the data 100 times. So we run it through 100. It sees every data point 100 times. So you iterate. And we use some regularization to prevent overfitting. So that can be a real problem with neural networks, is it can memorize answers, and that's not what you want when you give it new data, because it won't handle it. So you can regularize the network using these kind of L2 lambda regularization and dropout methods. And you can monitor the performance of the model here, accuracy with training batches. So as I'm feeding, training the model, I'm testing it as well with an unseen set. And you can see initially the model is randomized, and so you may as well flip a coin as to predicting whether it's positive or negative, the sentence you pick. So flip a coin, 50-50. But then after you train it train it with many data, you have 2,000 batches, 4,000, 6,000 batches, you can see it starts to learn, and you can see the accuracy starts to increase. And then eventually we'll get kind of a plateau here at 18% accuracy. So the takeaway message here was that we need to train sentiment models on domain-specific corpora. Generic statement models are prone to high false positive rates. We saw that with the Twitter training model. The automated speech-to-text capabilities of TalkIQ enable rapid acquisition of such domain-specific data or lexicon. Okay, we're gathering conversations all the time, so we have that data available to us. So then we can perhaps train bespoke sentiment models specific to a given domain. So perhaps this thing is not such a bad thing for TalkIQ.
When you say domain, how specific do you mean?
Yeah, well, we don't know. It's an ongoing thing. As we acquire more data, we'll get more insight into that. So all I can say now is if you go from, say, Twitter to phone conversation, that's a huge domain difference. Or if you go from movie reviews also to phone conversations, there's a difference. Not quite as great, but still a difference. Now, whether you go from a certain customer base to another customer base for a different company, I would imagine that would be closer. Yeah, I don't know what the difference would be.
Or different movie genres? Or
Yeah.
it might be just specific.
Yes, yeah, so I don't know what that means. Yeah.
Later on, transfer learning could be something interesting to look into, like once you guys have customers in 2 different verticals, to see whether you can put in a bit of very specific set and also model in one, and then use transfer learning to, get a better model. But on a new customer, because you wouldn't have, let's say it's your first customer in your vertical, you wouldn't have the economy here.
Yes, and that's something we've actually been talking about this week. Excellent point. Yeah. Okay. That's it.
Thanks, David. I'll tell you guys about some of the other projects that we're going on. So Curelet has been working on prediction, which I mentioned earlier. And I told you guys what the opportunity was, but again, it's just a series of calls that is destined to end in a sale, that's a close one, or failure results. And so what we wanted to do was quantify the health of opportunities. Of course, that can help forecasting, that can help going in and helping the accounts that are struggling. Very useful things to be able to do. So some of the features that he's been using, so skipgrams. So probably a lot of you are familiar with n-grams, perhaps not all of you are familiar with skipgrams though. So n-grams, to back up, it really, so for example, a 3-gram means that you're going to look at every triplet of words in a sentence, every consecutive 3 in a sentence. Whereas a skipgram means that you are allowed to skip a certain number of words between the first and the last. So an example is probably going to illustrate this best. So for the sentence, I am a student of University of Waterloo, the 1 skip 2 gram is generated below. And so you can see, for example, one of the most useful ones, I think, is student university, which is second to the end from the right over there. And so student university has 2 meaningful words, and in between of them, you have of in the original sentence. And so it's kind of nice that we got rid of because it's not a very meaningful word. And in addition, people could talk about it differently. They could say of the University of Waterloo, university, or they could just have right? I mean, so we're dealing with speech recognition algorithms. So sometimes words are dropped, sometimes filler words are added. So that degrades the quality of n-grams. So using skipgrams, they're more robust to that just kind of variance in the number of words that could be between 2 words. So some of the other techniques that he's applying. So on top of tens of thousands of skipgrams, we're using TF-IDF. A bit out of scope right now to go into what that is, but just at a high level, a technique for discounting terms based on how often they happen. So there's just a general observation in language that very, very common words tend to not be very meaningful, words like the and of, whereas words like student and university, they don't occur in every conversation that you have, and they're much more meaningful, right? So that's a nice sort of statistical heuristic that people have turned into the TF-IDF algorithm. And so we use this to transform our skipgrams and to give a lift to the ones that are more rare because we know they're more meaningful. Then we do some dimensionality reduction. Like I mentioned, we start with tens of thousands of skipgrams, and that would produce a really long feature vector. We have to do all kind of overfitting or regularization issues. So we try dimensionality reduction, and that helps a little bit to bring it down to a vector of 300. And then we use a number of classifiers. And some of them, like assembly Bayes, are helpful because we also get some interpretation of the factors in the end. So we can see for a given call or a given opportunity, not only the prediction, but also which are the factors which are causing us to have that prediction. So then somebody can go in and say, oh, all right, the customer asked for a free trial 3 times. Yeah, that's a good thing. That does indicate probably. Or if it's something negative, perhaps the manager can go in and either talk to the rep about a pattern that they're seeing or go in and resolve the problem with that account, potentially. And so Cindy's been working on our active learning framework, which perhaps gets to, I think, the question that we had up there. So this is a way for us to really get the most recent data in our training set, in our test set. So the way it works, we have a number of models that are running in production. Some of them are in dark mode. So their outputs are not going to customers. They're running very similarly to the live models, but we're just dumping them, recording them, logging those events. And then we send those events, or we send a subset to those events to Scale API to get labels. And those people will tell us what is the accuracy, how well are we doing, were these false positives or not, for example. And so then this allows us to determine, a test accuracy, just how well are different algorithms doing. Is the best one the live one at a given time? That's a useful thing to know. But also it enables us to gather the sort of freshest data for training, right? So that's the general principle. One other remark is that it's suboptimal to send just a random sample of your data to Scale API. It's better if you can pick the data that's near your decision boundary of your model, because then your model is going to learn more from that data. So we look at the probability, or in some cases the uncertainty of the model, and that helps us just be more efficient in terms of resources. And Mata has been working on punctuation. So of course, as you can imagine, when you get a speech recognition output over a whole conversation, you probably want some way to break up the conversation. So some of that is provided speech recognition, right? There's pauses. We actually have 2 separate channels if there are 2 speakers. So we know, when we can sort of aggregate based on pauses from the speech recognition output. But then beyond that, it's nice to have punctuation. So that just helps readability. But the even bigger application is being able to know when questions are happening. Whether you're in sales or especially I think if you have like a customer support group, if you know the types of questions that are coming up consistently and can classify those, that's very valuable information. That really tells you what your customers care about. It's a little bit buried in the detail of the pitch or something, and if you can bring that very meaningful information to the surface, it's useful. So for that, she's using a bidirectional LSTM with an attention mechanism, and that is able to infer if it should be a space, a question mark, a comma, or a period. And it's based both on the words themselves and also the pauses that we get from speech recognition, which makes a lot of sense because if somebody's asking a question, they probably are going to pause afterwards, otherwise it's a rhetorical question. And if people will usually pause a little bit after a period. So there's really interesting information in the pause duration there that can be put to good use. Okay, I guess that's it. And yeah, this is just an example of the output of the sentiment model on this sentence. So just showing sort of the words that are found to be most positive. So I hope there's of course positive expressions. That's it. Questions?
In the end there for punctuation, are you guys using Scale API to get the data set for that?
Yeah, we are, but actually what we were able to leverage was all the previous work we did for speech recognition. So when we did speech recognition, people, when they spell out transcripts, which is the training data for speech recognition, they will just naturally punctuate because we didn't tell them not to, and we started to realize also, hey, one day this could be useful. So we have all this massive training data from there.
They're doing like an anti-pre-processing step, by putting punctuation in, but yeah, it's very useful now.
Yeah, and we also used some other data sets, so we were able to combine, I think, the Euro Parliament data set with what we were using, and that has a lot of questions in it.
Is there any literature on that, the punctuation?
Yes, there's a paper I can help give you the reference afterwards.
How do you encode the pauses for your neural networks? Like you said, when two people are talking, there are pauses that may imply a question or something like that. How did you encode it for your machines to get on with it? So like you got the pipeline says you got a speech to text recognition, and then you got the neural network model that is actually giving you the sentiment. Yes. So there is some data lost when you are converting from speech to text. Apparently you are capturing the pauses, but then when you have the text, you have the word embeddings. So are you constructing maybe embeddings for the pauses, or? So
in general, the embeddings don't have pauses.
Yeah,
it's just for the punctuation output that we keep them, and that's separate. So that's a whole separate training step. So there's a first step that's training just based on the words.
Okay.
And then after that, it's a separate training step that's just new pauses.
Cool. Thank you.
Are you aware? Regarding my previous comment about the fact that sometimes these models are not bulletproof. Yeah, I mean sometimes they make mistakes. I was reading that someone was suggesting, and then I've seen an article saying that maybe we should marry the linguistic approach with this neural network statistical kind of a way to get better results. Are you aware of any work in this area?
So what do you mean when you say marrying linguistic and neural network approaches? What do you mean by linguistic?
I mean the initial approach.
Like the engrams, based language models?
No, I mean the before neural network. Yeah, the last artificial intelligence winter, yeah, was caused by the failure of expert systems and
really understanding what sentences, not only basic statistics, but really understanding.
With linguists working in your team.
Yeah.
Like object, subject, what is the
and
structure of the sentence. Yeah.
Or rule-based systems that would follow formal linguistic
Gotcha.
Down enough grammars and things like
Gotcha.
that.
I mean, we haven't done that. One reason being linguists are very expensive, and at a startup, it would be difficult, I think, to do that. And I imagine we can also purchase like already labeled corpuses if we needed to. But I mean, there's another thing about speech recognition, which is that often people don't speak in grammatical sentences when they're on the phone, right? I mean, we listen to these conversations, and there's a lot of restarts, people sort of interrupting each other, a lot of, yeah, oh, I'm sorry, go ahead. So it's just it's not like reading a novel, that's for sure. And then there's, of course, errors in the speech recognition output as well. So to put a parse tree on top of speech recognition is very challenging. And as you know, it's already a challenging problem to start with. So we decided not to go that route.
It's not the trend anyway. Like I can say Microsoft was working on hybrid systems maybe 15 or so years ago, not with neural networks, but with other approaches of machine learning hybridized with formal linguistics and rules. But it's, and I'm sure other places were too. It's just very expensive, as you said. You're talking about how do you get all this labeled data for what you're looking at. Imagine getting all that data in terms of what are the parts of speech and all the things that you're tagging the sentence with, the parse trees. It's an expensive process.
There are some approaches that use existing parse trees. I mean, so like Richard Soker works a lot with. So he has like a tree LSTM algorithm. So for that, it is an LSTM, and but I guess it's a recursive neural network, not a recurrent neural network, and it's actually looking at the parse tree. But the parse tree is not labeled by a human; it's estimated. I think those algorithms they're more than 95% accurate these days, I believe. Parts of speech tagging. So that's an alternative route that can work. But yeah, for us, it really was also just the speech recognition output is not as parsable.
I know it's a long shot, but any chance that you're going to go for charity and release some of the data that you've transcribed, or is it too sensitive?
Well, I think, the question would just be, are there privacy issues?
Right.
But yeah, otherwise, we would like to. I mean, we use a lot of open source software and open source data, and it'd be great to do that.
Yeah, I would definitely like that, and I'm sure a bunch of students from the University of Waterloo, from your example, would also like that.
Cool. I mean, yeah, it'd be worth like having a conversation about it.
Yeah, sure.
I think it would sort of be on a customer by customer basis. Like some of our customers, probably most of them would care, but some of them might not have any issues with that.
Right. But do you know overall, is it even possible for you to say, okay, like the conversations 1, 2, and 3 don't care about their privacy, they're fine with releasing their conversations, and we can release them. Or it's like very random. Some people may care and some people may not, and you don't have data about that. Like you don't have.
I don't know. I think almost all conversations there would be some kind of concern, because it could be just the name of somebody who's making a purchase. It could be a company not wanting to reveal their practices to competitors. So I think that's one of the reasons there is no like sales data set out there, which is one of the reasons we have to build our own, which is both difficult but also barriers to entry.
Did you consider having the salespeople tag the sentences at the time? Like sending them out to a third party seems like an extra step where you just have like a
when you have the expert right there, you could do it, right?
Yeah, maybe. I don't know. Maybe there's some reason that's not a good idea.
I just don't think they would want to. I mean, so for example, they use Salesforce a lot of it, right? And so even in Salesforce, there's a lot of Salesforce makes them label certain things. So they have to, enter at the end of the call, this was successful demo or stuff like that. Even then, looking at that data, there's a lot of mislabels, and that's something they're very strongly incentivized to do. They've got somebody, going around and making sure to do that. So yeah, we talked about it, but we really got the sense that they wouldn't be doing it for us. That we'd be better off, paying somebody to do it.
So what are some of your biggest challenges or bottlenecks besides like obtaining labeled data? Sounds like it's one, but what about things like, you mentioned the Gaussian naive Bayes approach, you're able to get some insight into why decisions and classifications are made. Is explainability a challenge for you too when you're using neural networks?
Yeah, it can be. It can be. I mean, one is definitely like going from between organizations. So there we don't have a very strong sense yet of, you know, how much can we generalize from the companies where we're doing very well to new companies where we may not have a lot of data. It definitely requires work to customize models, right? And as we scale, we don't want to be customizing models to every organization. So it's sort of been a pretty strong constraint for everything that we do to try to make sure as early as possible that we're going to be able to generalize it to other organizations, that it doesn't require a lot of training data. So yeah, I think that's one of the biggest constraints that we face.
I'm interested in the accuracy of your speech recognition algorithm. Another question I also have is that, so if I were in customer support, rather than the sentiment analysis, I would be more interested to know what are the particular topics of concerns of people. For example, website is unavailable, or they could not get timely reply, or there are some other problems. So do you do this classification?
Yeah, no, that's a great observation. So for the word error rate, so right now I believe we're at 8.8% on our clients' data. For 8.8. And for the topics, yeah, that's true. So we have, I guess we have two approaches to that. Well, I mean, the main one is, I think what we're hoping is that once positive, essentially flagging positive sentiment is highly accurate. What we'd like to do with that is look for correlations with various topics. So if you know that if you can capture positive sentiment, you can capture negative sentiment, then you can look for regions of overlap with topics. How often does positive sentiment correlate with this topic and this one? So that's a way that we could get to that.
Sometimes I guess it's just maybe a different problem here in analysis to do categorization. And it may be even easier to do than.
Can you think of a way to do sort of the two problems at once? Is that what you're thinking?
Sorry?
Were you thinking of a way to do the topic analysis and sort of the sentiment together to know? It sounds like maybe that's what you had in mind.
No, I'm saying it's different problems.
Yeah, that's how we think about it. Any other questions?
How about the ability of the system to explain why it reached this conclusion? Yeah, I remember when it was the Google Go challenge, yeah, when I think it was in the round 3 when the system made a move that everybody was thinking it's stupid, but actually it was a winning move.
Were you watching the games?
No, I was reading about it, yeah. And I remember reading also about this issue about the issue in the neural networks from the linguist point of view is the system cannot explain why it reached that conclusion, yeah, logically.
Yeah.
You know, so do you know is any?
Well, my background's in neuroscience, and there's a very interesting theory in neuroscience called the interpreter theory of mind. And that's the idea that we commonly just make up explanations for why we do the things we do. That is, we think we know why we do what we do, but there's a lot of evidence where we don't. There may be very limited access between the part of the mind that rationalizes and comes up with an explanation and the neural network, which is a different neural network that produces an action.
But a mathematician can explain you in the logic steps how it proves a theorem, yeah? I mean,
that's true. But there are computer algorithms that can deduce theorems as well, right?
Yeah.
But for things like perception, like that's not a good example because in math, you do that. Like Wolfram Alpha will show you the steps. But for perception, I 100% agree with that theory because it could be like TensorBoard, like where we explain our, like we'll explain like why do we think this is a cat. But that's after the fact, right? Like our neural network already processed that it's a cat. So arguably that,
They're different modules.
Yeah, then like the explanation is like an afterwards, which is similar to looking into a neural network afterwards and trying to figure out what it's doing.
Yeah, I mean, if you think of evolution too, we evolved to do things and not to really to like think about them afterwards. I mean, that's very recent human evolution that performs that task.
So you might have a system on top that could tell you why it thinks it happened, but it might not necessarily be the explanation.
That's what
Although that could still be of some value if it somehow informs a customer why something happened and it meets whatever needs they have.
yes.
It just wouldn't necessarily give you insight into why your algorithm gave you a certain output.
Probably wouldn't want to advertise as doing that.
No. But it's true, like if you look at a letter, you could say, well, how do you know that's a letter A? You don't, like if I describe that to someone, I'd say it's an upside down V with a horizontal bar, but that's, when I see an A, I'm not going through that deduction when I see it. It's just, it's a recognition of some pattern.